Hello, Robertus. Can you hear me?
Hi.
Hi. How are you?
Very hot.
Okay.
Almost as hot as in India. Hi, Dipu.
Hi. Come
Hi.
here to Nainital. It's very pleasant here.
Dipu, it is 38 in Hungary.
and in Belgium, it is flooding also. So
I mean, England and Belgium is
yeah.
like I think 16 degrees was the temperature in the last few weeks. 16 to 18.
Yeah.
I just spoke to Misha because I asked him how is it in Sheffield, and he said 18, 20. But here it's also it's very unusual. This is now the third week that the temperature is above 35, 36, 37. Normally we have it for a couple of days, even 40 or 42, but not for such a long period.
Okay. Yeah, I remember I also had a good, hot, Budapest in my memory. Beautiful, but
you're used to it, right? But I think for the third week now, it's too tough and no rain. And when the rain comes, it comes so violent. Like I don't know if you have seen it in the news. Not far from here, maybe 200 kilometers. So the ice is normally like a centimeter or half a centimeter normally. But now, in the last few weeks, there was ice with the size of orange. Diplo, this kills you.
Wow.
No one died, but 200 houses were destroyed. I mean, imagine, would an Indian house survive an ice with a ice fall with an orange? No, that's not. We are not designing.
We get a hailstorm in the hills. We do get, and the cars gets a little damage, but not of that size, of course.
Dipu, yesterday in Italy, not far from North Italy, yes, all the cars on the highway, I don't know how many hundreds of cars, they all were destroyed, all of them. Not a single survived. I mean the windows. Yeah. Because the ice was a size of a 5 centimeter diameter. 5 centimeter. And in north, not north from here, around 100 kilometers from the border, we had tornadoes. They never had tornadoes in history, living history, never. So I think something is going on.
Yeah, not the sun, but not the sun. Sun should not be blamed for this, but I think humans can be blamed.
I agree. So you have good weather in Nainital?
This year, actually, the rain is seems to be a little more than last year. I mean, I have a small data points, but if I compare with last year, at least the rain is more. And I think in general in India, the rain predictions are better this year. Hopefully, it won't be too much floods because we do need rain for our good crop, but not for. Yeah, I think it's getting time.
Yeah, I was about to say that. Okay, so Robertus, you may share your screen and then I will introduce you and then we can start.
Share screen. Yeah, 1 sec. I think I just shared the entire screen. That's the best.
Yeah, that would be better.
We'll see how it works. Do you see this?
Yes, we can see your.
Let's continue. And do you still see?
Yes, we can see the full screen as well as your presentation in full screen.
Do you see these pictures like me, you, and Dipu, and Arias, and Abi, and all this?
Yeah. I mean, it depends. Yeah, I can see it because mine is not like full screen, zoom in full screen, but I can see you, your video. Yeah. Okay. So I think we should start now. So good afternoon, everyone. Welcome to the Aries Astrophysical Seminar. And we are very happy to have Professor Robertus Erdelyi with us today. Professor Erdelyi is a professor of mathematics at the School of Mathematics and Statistics in University of Sheffield, UK. And today he will talk about MHD waves and oscillation in the solar atmosphere. So Robertus, over to you, and you have 45 minutes, and I will remind you after 40 minutes. So.
Okay, thank you very much. Also, thanks for this invitation and this wonderful opportunity. Actually, I do mind a little bit because I would have gone to India, even just for a seminar, especially to Nainital. I have been there before. It's a beautiful, twice actually. It's a beautiful place, but I think now it's not realistic. We cannot travel, right? It's impossible. I know that Raul, one of our postdocs, he just wanted to come to the UK, and it is so complicated. You know, when you return, he had to go to quarantine and government hotel, £150 a night, and it's a nightmare. So no travel, unfortunately. Anyway, thank you very much. And also, I would like to openly congratulate to Deepu, because we have not spoken since he is the new boss in Nainital. So it's a new era, I guess. And I see that you're very active. Seminars are going on and well organized, and all these Facebook activities, etc. So looking forward. I hope that you will be there for a while. I hope that these restrictions will be gone, and then I can visit you in person. That would be really great. So thanks a lot. Today, I would like to give a kind of review presentation with some snippets on some results or questions on waves and oscillations. This is one of my my own favorite topic. And before doing that, I just would like to thank for all the collaborators I had. Many PhD students, actually over 50 PhD students I had in my career so far, and 25 PDRAs, and they all contributed in various ways to this, what am I going to show you today. Do you see on your screen these long, you know, the pictures? Do you see that? You know, like me, Deepu, yourself, or shall I close this?
No. We are not seeing on your presentation. I can see it on my window.
Okay.
But not on your presentation.
Because on the side I have this list of people who are on the call, but you don't see it. It doesn't shield the presentation. Yes.
No.
Okay. Good. Then we just continue. So thanks to all these colleagues. I would like to raise right at the beginning some big questions. What I think are some fundamental questions in our area, and then I try to answer these questions or explain that how far we are in answering these questions. I have done this a few times recently, and the reason why maybe you have seen these questions before, but I would like to emphasize these questions because I think they are important for the context. And anyway, partially the talk is a kind of summary of where we are with this wave and oscillation story. Those who are maybe less familiar with the waves and oscillations, when I was a postdoc myself, some more than a solar cycle ago, I'm afraid, I remember I went to a national astronomy meeting. I went to our national astronomy meeting. It was in St. Andrews, and one of the UK eminent professors said, actually, there are no waves on the sun. It was, in my opinion, this is never a good idea to say there is something does not exist, because later or sooner or later people discover these things, but forget that. But the not good part of the message was, in my opinion, but there were all these potential referees for our proposals, and if you know, if a prominent person says there are no waves on the sun, and then next day or a month later you submit your proposal studying them, that's not a good thing. But anyway, this is how it all started in the mid 1990s, that there are no waves on the sun. And what I think now is maybe there are too many waves on the sun, and how this story evolved, that's what I would like to explain a little bit. And that brings us to the first question, that how close we are actually to solve one of the greatest problems of astrophysics, which is the abnormal, but in parentheses abnormal, temperature distribution of the solar atmosphere. We are going away from the heat source, from the energy source, from the core of the sun, and in spite of that, the temperature starts to rise in the solar atmosphere. So how is that explained? How close we are to solve this problem? If you go on the internet and check any major solar projects, even plasma projects, astrophysical plasma projects, you will find as one of the key questions is usually to solve this abnormal temperature distribution. So have we actually improved our understanding since this question was first raised about a good, by now, almost 100 years ago, actually. So that's an interesting thing. I believe that we have made some progress. We know now what is the source of the energy. We may know also how this energy propagates, but we don't know how the energy is actually dissipated in the corona. So, you know, the first two questions of source and means of transporting energy from the core into the atmosphere seems to be now kind of settled. There are still some details of how exactly the energy propagation is, but I think we are now getting closer to the solution. However, I don't think we have made too much progress in the dissipation process itself. And I think this is important because if we want to have any link of our research to, you know, impact, which is relation to the society's daily life, then we would need to understand the dissipation part and reproduce it. And I don't think we are very much progressing with that. Okay, so that's the first question. The second question is that what's the role of MHD waves in this heating process? I am actually bouncing back now the question to this eminent UK solar physicist, and I think he was wrong to say that there are no waves on the sun, because there are many waves on the sun. We interpret these waves these days as MHD waves. This may not be entirely right. It could be that we have to go beyond the framework of the MHD, but I think the MHD is going to give a pretty good first insight into the modeling of this wave propagation. So there are waves, and the interesting part is that there are too many waves. I will come to that a little bit later, but if you look at now the wave spectrum, you work out the energy in various structures on the sun, you will see that the amount of wave flux is actually much more than you need to heat, not just the corona, because for that you don't need a lot, but the interesting bit is that we observe these days waves so many, or so much wave flux, that we can easily heat the corona. So what happens to the rest of the energy, you know, the excess energy? And I think that's a question where we may see some surprises. Okay, and the first question is that what can solar magneto-seismology, SMS, offer to us? How does this question come in? It's because waves, it's a general thing that if a wave propagates in a medium, then the wave actually carries information about the medium. So not just that the wave carries energy from, or information from place A to place B, but this information is actually modulated by the medium itself. So waves do carry information about the medium. And if we have the right tools, in the case of solar physics, it's called solar magneto-seismology, because the waves are highly magnetically dominated or magnetically influenced, then we talk about MHD waves. So solar magneto-seismology with the right tool can enable us insight into sub-resolution. And I think this is a very important point here, sub-resolution, because, you know, we can build the IBIS, we can build the National Large Solar Telescope in India, we can build the 8-meter giant solar telescope in China. There is always this resolution issue, and we will always be bounded by resolution. And I don't think that, definitely not in my lifetime, maybe in one of your lifetimes, we will be able to go down with resolution to the level where the actual dissipation happens. But I don't think this will happen too soon. So then how do we learn about the dissipative processes if we are not able to observe them? Well, solar magneto-seismology is a way or a tool that may allow us to gain information below resolution. Okay, yes. So what's the problem? The problem is, let's just look at these two pictures. On the left-hand side, we see satellite observations actually. These are the coronal loops. I think this is AIA, so it's an SDO image. And on the middle and the right-hand side, the gray, so the black, white, and gray scale is the magnetic field. In the middle and the right-hand side, I'm using the same magnetic field, and I have got the magnetic field information at the surface of the sun. And then I try to construct the magnetic field, how the magnetic field could be in the upper part of the atmosphere. And here comes the big problem. The problem is that we have information about the magnetic field routinely only at the surface of the sun. So we don't have, believe or not, and I don't understand how this shortage is never really addressed, we don't have still, although we do solar physics from space, I would say in the late 1970s, properly, no Skylab, we still don't have a routine observation of the solar magnetic field above the photosphere. And there are some instruments who from time to time do measure magnetic field, sometimes occasionally, sometimes for some period of time, but we do not have a systematic magnetic field observation in the upper parts of the solar atmosphere. Now we know that in the corona it's difficult to do these observations, and I fully understand it. But the corona is, in my opinion, is only the tail of the story. You know, it's like the icing on the cake. If you want to eat the cake, first you need to make the cake itself. And the icing is important, but you know, at the end, the cake will give you the real taste. So why we neglect, why we don't address this issue to measure the magnetic field routinely in the lower solar atmosphere, so that then we can construct in a unique way the magnetic field, that I think is a shortage. And these pictures demonstrate this. So the left-hand side, do you see my cursor if I move my cursor?
Yes, yes, we do see.
Okay. So on the left, thank you. On the left-hand side, you see this two-dimensional image, and in the middle and the right-hand side, there are two extrapolations of the same magnetic field, but using different approaches. One is a potential field approximation in the middle, and then the other one is so-called nonlinear force-free approximation. And you can see that for the same input data, I have got different outputs. The magnetic field output is different. Now, if the magnetic field output is different, then how can I then, you know, with high confidence, talk about dynamics of this magnetic field? And that is, I think, a problem. Now, of course, for certain specific studies, like you know, studying specific loops or prominences or etc., we may overcome this problem by having magnetic field observations, but you know, we don't have these observations routinely, so we don't have a routine construction of the solar atmospheric structure, and I think this is a problem. So how to get around this? Okay. Well, let's give a little bit of a historic background. When I was a student, I studied that the sun is, you know, we have the solar surface, and then we have magnetic fluxes coming out. And an image like this was the magnetic building block of the solar atmosphere. You know, sunspots, we mostly spoke about sunspots at that time, and it's a nice, well, it is a uniform picture more or less, but even if there is some non-uniformity, this was the fundamental idea that this is how the atmosphere looks like. And then some years later, another picture emerged that actually there is this continuously emerging magnetic carpet, if you like, which replaces itself. And I think in the TRACE time, and TRACE was an excellent US satellite. In the TRACE time, the replacement was estimated to be around 14 hours. I think today we estimate it much less. So we have all these various thick and thin and large and medium, large or small loops, the magnetic carpet, beyond these nice big loops, the normal coronal loops. So that's the next kind of sketch of the building block of the sun. And then I think another maybe not 10 years later, but a little bit later, we came up with a suggestion that we should add to the static picture some dynamics. And the dynamics is due to the interaction of the magnetic field. So in the middle, you see an example of that, there is this current sheet form, because if opposite polarities of magnetic field meet, then current sheet forms and you can have the reconnection. This is one type of dynamics. And the other type of dynamics is the jets themselves. And the jets can propagate along the magnetic field lines. So we suggested in about a good 20 years ago, almost, well, in 2 years, it's 20 years ago, that this could be a kind of building block of the solar atmosphere. Let's try to study a building block like this one. Let's try to use, if I'm now speaking in terms of modeling, let's now find the eigenvalues of a model like this, which would mean that I work out what are the fundamental units of any perturbation. Any perturbation could be seen as a superposition of these eigenvectors. And I think this is a very difficult problem. I don't think we are too close to have an eigenvalue of a building block like this one, but that is what eventually we should get if we want to understand the physics in the lower solar atmosphere. And then came Wiedemeyer-Böhm, swam with a very complicated, but I think a beautiful picture. In fact, just about this picture, one can talk an hour. I don't want to go into the details. It's a very highly skilled image of bringing together everything what we have on what is fundamentally important for solar physics. We have the field, the fibres, the jets, the speckles along the fibres. We have the open fields, we have closed fields, we have the shock waves here, waveguides, etc., etc. Alpine waves, various type of speckles, slow speckles and fast speckles, etc., etc. So this is a nice cartoon, and if it was a summer school, I would probably take this picture and talk about much longer, but we have no time for this now. And there is a simplified version of it. I don't know why my cursor sometimes is not working. It's this one. So Robertus came up with almost the same picture as this big, nice color one here, some years earlier, about 2 years earlier. And in my opinion, this picture also contains all the elementary parts of solar atmospheric physics. It has the open field, the closed field, the jets, etc., etc. Sometimes we say that there is no Nobel Prize in solar physics. That's unfortunately true. But if there was one, and I would probably nominate this picture, this black and white picture, not the color one. The black and white picture I would nominate for one of these Nobel Prizes, because this contains so much information. It seems to be simple, but if you go into the details, it contains so much essential information about our modeling of the lower solar atmosphere. Okay, so that's our model at the moment. That's a nice two-dimensional model. Of course, you can make it much more complicated. You can make a 3D version of it if you wish. But that's where we are from an understanding perspective. And then I can ask you the question, what do we see? Now, what we see is something like what you can see on these two movies. Let me just run both movies. It's a highly dynamic, continuously changing, no statics is there. As you see, it's a highly evolving, very inhomogeneous medium. And that's, I think, our big headache. Let me just run this movie again. That we have a highly inhomogeneous, structured and stratified solar atmosphere. Now, to work in this and to explain these beautiful features here, coronal loops, loop oscillation, coronal holes, active regions, etc., is very, very complicated. And on top of it, it's hot. So that's what we actually see. But if you go into more details, then these loops will have substructures, if you like. And just have a look of this well-known movie where first maybe not first, but in this context first, EUV oscillations were reported. This is a typical example of how solar oscillations can be studied. You study the amplitudes and you retrieve this, you invert this information, and you try to derive diagnostic information about the oscillatory waveguide itself. It's not an easy task. So the flare is emerging here, and the flare kicks the loop, and that's the reason of the oscillation. And here is another one. I don't know whether sound will come across. Let me just play this. Wahab, could you please tell me if sound comes across?
Yes, we can hear. Yeah.
Okay, so you will hear a lot of noise now, but I will do it on purpose. I will run it twice, okay, if I can. Let me just... Let me run it again. You see here the surface of the sun, and on top of it there is a loop, and then this loop is contracting, expanding, contracting, expanding. So it's a sausage oscillation. Okay, so what you have seen now was, I think, the first type of sausage oscillation reported probably, I don't know how many years ago, good 10 years ago, or maybe more. And we turned then the visual information, we turned it into sound. So we accelerated a little bit the frequencies. And then we had a press release and we called it Heavenly Music of the Sun. And the funny part of the story is that maybe half a year later, I got a letter from the American Bible Association. You know, this story was picked up by a lot of newspapers and journals, and I remember even Indian Times has reported it. But that's not the point. The point is that I got this letter from the American Bible Association, you know, Sarah Palin. If you remember her, she also ran for presidency when George Bush did. And at the end, she was the president of Alaska, and or governor of Alaska. And I got this letter, and it says my name was correctly written, and you know, I start to read it, and it says that the message was that they thank that I have provided a further scientific evidence of the Bible, and that really has, you know, the Christian holy book, and that really has surprised me, because that's definitely not the intention when we made this press release about this coronal loop oscillation. And then when I read the letter a little bit further, because we called it heavenly music, and this phrase appears in the Bible itself, then they interpreted this as a kind of scientific proof that the Bible is correct. So, you know, just be very careful when you do press releases and how you do the press release, because this can be really distorted. So that's all the message. Anyway, this is what we see, a beautiful oscillation. It's another example here. Again, a localized twisted oscillation or oscillatory motion. That's actually a solar tornado, and it's a big one. It's not easy to see these big ones. At the time of observation, the chance was 1 to 1,000,000. Now, because of the satellite technology, we have much higher chance to see them. But again, I think this is a building block, because these type of phenomena represent one particular waves, which is what are very difficult to observe, and those are the Alfvén waves. I will come to that. Alfvén waves are purely magnetic oscillations, and I will come to that. Okay, and I think this is the last image. Oh, sorry. I would like to show you how structured and how dynamic the atmosphere is. This is from the limb of the sun, and then you can see all these loops emerging, and there's little tiny jets, the spicules. What I believe now myself are probably the holy grails of the solar atmosphere. So it's not anymore reconnection, I think. What I have been told many times, I don't think reconnection is so important for solar atmospheric dynamics or heating. It is important, but it's not fundamental, in my opinion. So what you see here is all these jets appearing. So that's what we see on the sun. And then the question is, okay, nice. So how can we build up a building block? And how can we, by analyzing all these observations, how can we answer these three big questions? You know, the heating question, the diagnostic question, and the wave propagation. So how we can find a unified framework to address these questions. And what I'm going to do now, I will answer the questions right at the beginning, and because I'm sure I will run out of time, but at least you will have answers to these big questions. So let's now answer the first question in context of solar magneto-seismology. I think we made a big progress that we don't believe anymore in these monolithic structures, but we can clearly identify the thread-like structure. If any of you has listened to John Schmaltz's talk, I think 2 weeks ago, the ISSI talk, then maybe you have seen how much she argued by looking at, she studied the loop emission and whether this is coming from threads or a monolithic one. I will not go into that aspect, that's her area. But looking at the problem of seismology point of view, now we know that it is, we have a very highly structured medium. And this is the important bit, a structured medium, not just stratified, but structured medium. So we are able now to identify stratification and structuring in density, temperature, even in magnetism. So depending on what instrumentation you have got, you are able to identify basically very localized waveguides. Within that, you may assume there is some uniformity, but bigger structures like prominences, sunspots, even magnetic breakpoint are made of many little fine structures. And the issue is not just that we have stratification, but we also have the radial structuring. And I think this is important because the radial structuring will help us to understand the dissipation. The fact that we have got longitudinal stratification is not so relevant for dissipation. Unfortunately, very often people mix this up, even in the audience, and I'm not going to say who that is. There are people who actually assume that the longitudinal stratification is relevant for dissipation. Unfortunately, it's not. Energy will be lost because of the radial stratification, and the radial inhomogeneity is what it matters. And then there is another big progress, I think, and there we really made progress, and that is the time dependence of the waveguide. So the waveguide should not be seen as some kind of static medium or a static structure, but they live. They have their own lifetime. Now, lifetime matters if the perturbation, the characteristic timescale of the perturbation is actually comparable to the waveguide's lifetime. Then we have an issue. And I think that is an extremely difficult problem. From a theoretical point of view, only very few steps are made in this direction. But from an observational point of view, just if we recall some of these movies I have shown, we have seen that the dynamicism, the dynamic structure of these waveguides is there. So do you want to make real progress? Okay, let's now focus effort on understanding the time-dependent waveguide structuring and study wave propagation in this medium. So that's a difficult thing. Then, of course, we should mention also the context that, you know, we interpret mostly these waves and oscillations on the sun in the MHD framework, but that's not the right interpretation, because we have our neutral, not neural, neutral collision, and we should, I misspelled here the word, it has to be a neutral collision. So yes, there is this issue that the ions and the neutrals are important, because the neutrals will not follow the magnetic field line. There is no frozen in low or frozen in condition for the neutrals to obey the field lines. And that, I think, is an important thing, because mass, momentum, and energy can go in other directions. It's not necessary that the magnetic field line will be a waveguide. And that direction is an interesting direction, but for that we need good resolution. We need very good time resolution, which has to be, for instance, at photospheric level, it has to be sub-second. Now, Dekist probably, not probably, Dekist does provide this type of timescale, and EST, if we ever build it, will also provide this timescale. So yes, there are boundaries of there are now realistic challenges of the MHD boundary. For instance, the ion neutral collision studies, and of course there could be many other things. What I just put here 3 question marks. The so-called unknown unknowns. We don't even know what the answer will be to questions what we can't even raise because we don't know the questions themselves. Okay. Can you still hear me?
Yes.
Because my computer is now okay. Now it works. Doesn't. Yes, it works. Okay, next question. We had 3 questions, and the next set of questions. And the next question I would like to answer. It's about heating. So what progress we have made? Where are we with the heating issue? And I think this is really interesting because when I started all these things 20-some years ago, I studied at the university that the sun is a kind of homogeneous, not so much structured atmosphere, and then these acoustic shock waves are there, etc., etc., etc. What we know now is that it is likely that different magnetic structures are heated differently. And to this audience, I can give this specific example. So, for instance, magnetic bright points seem to be heated by alpha waves. Magnetic pores seem to be heated by sausage waves, MHD sausage waves. Motors or spicules, they seem to support mostly sausage waves and a little bit of kink waves in terms of heating. Fibrils, however, seems to be supporting mostly kink oscillations and a little bit of sausage oscillations as well, but the emphasis is on the kink part. Or if I take a pore with a light bridge, it looks like that the m equal to 1, not kink oscillation, but alpha wave is present, and maybe they are responsible for the appearance of this high emission. So heating seems to be almost structure dependent. And I think this is an interesting thing because it looks like we will not have a uniform theorem, a general uniform theorem, which will explain the high plasma temperature in the atmosphere. Different solar atmosphere. Different solar atmospheric structures may be heated differently. And it's also good news in a sense because we need to understand why this difference. I think that in my personal opinion, the difference lays in the structure itself, how the structure is constructed, low beta, high beta, etc., etc., and that will be the selecting factor. But if you ask me why motors are heated mostly by sausage waves and not so much by kink waves, on the other hand, why fibrils are heated by kink waves and not so much by sausage waves, I can't answer you that question at the moment. So there is some debate here, and I hope we will be able to progress. Okay, so let me show you some movies now. Where are we from a theoretical perspective? What you see here is the basic building blocks of a theoretical interpretation, and the simplest building block is a magnetic slab. On the left-hand side, you will see the so-called sausage oscillation in a magnetic slab, and I'm going to run the movie. And on the right-hand side, you will see the kink oscillation of the slab. The main point is that the sausage oscillation will not displace the axis symmetry, or the x-axis of the slab, while the kink oscillation does displace the axis. That's the main difference. Of course, these waves could be slow waves. These waves could also be fast waves. They can be surface waves. They can be body waves. So there is a lot of variety here. But from an appearance perspective, they are either symmetric or antisymmetric. And these are the building blocks which are very often observed in a solar structure. Now, if I now go into cylindrical geometry, which I think is an improved version of the slab geometry, then the sausage oscillation is on the right-hand side, and the kink oscillation is on the left-hand side. I don't know what parameter is now here shown. Maybe it is temperature or density. I don't remember now, but it doesn't matter because for magnetoacoustic waves, these waves will perturb all these physical quantities. So again, these are the building blocks of these are the fundamental oscillations of a magnetic cylinder. And we like to assume that the solar atmosphere is made of many, many cylinders. So we need to understand then the properties of these waves and oscillations. Now you can add a little bit of complexity to this problem if you twist the magnetic field. Now, maybe if you recall the image when I showed you this magnetic field extrapolation, there didn't seem to be too much evidence of twisted tubes. But the fact that you don't see this twist should not make you biased towards that there is no twist. In fact, my understanding is that every flux tube has a twist. Maybe that twist is small, maybe it's a 10% or maybe 5%, but every flux tube is twisted. That means we have to look into the MHD spectrum, what type of waves and oscillations are allowed in a twisted magnetic flux tube. And that work we have done in Sheffield. I think I think we have solved explicitly the twisted flux tube problem, and we have identified, of course, in some geometry, but we have identified the existing MHD waves in a structure like a twisted flux tube. So, and I consider it as a not so simple problem. If you are a little bit mathematically inclined, then the slab geometry is mainly described by trigonometric functions, tangent and cotangent hyperbolic function. If you go to cylindrical geometry, you will have the Bessel functions. And if you go to twisted magnetic flux tube, then you will have the confluent hypergeometric functions. And that's exactly how mathematics is building. The Bessel functions are the generalization of the trigonometric functions, and the hypergeometric functions are the generalizations of the Bessel functions. So it's very interesting how by adding complexity of the flux tube, how we actually follow the structuring also in pure mathematics of these functions. Anyway, twisted tubes have been studied, and I don't think that we are yet there at the moment. We analyze the characteristics of MHD waves, or we derive from observations of MHD waves. I don't think we are yet there that we derive deeply the way flux tubes are twisted, but this is a resolution issue, and sooner or later we will come to that. How important the twist is in the heating, that's, I think, it's a very important question. In my opinion, again, this is my personal opinion, the story of twist will change the story of heating, but I cannot go more into that at the moment. Okay, then comes the next level of complexity. Why should our waveguides be symmetric? So I'm just going to demonstrate this for you for the slab geometry. On the left-hand side, you see kink oscillations, and on the right-hand side, you see sausage oscillations in a waveguide, such that on the left and the right-hand side, the medium is not exactly the same. It's an asymmetric environment. For instance, I can take a light bridge, or I can take some slab structure, like a magnetic slab structure, a magnetic bright point, which is elongated between convective cells. And on the left-hand side, why should the density of a convective cell be the same as on the right-hand side? Of course, it is not. So if there is difference in the equilibrium, then the oscillations will be affected by this. And that story we started a couple of years ago, and almost all of my PhD students in the last couple of years work on this idea of asymmetric MHD waveguides, and the visualization of the two well-known waves. On the left-hand side, once more the kink, and on the right-hand side, the sausage waves are shown here just to show you how asymmetry influences the waves. Okay. Now, this slide is very much crowded on purpose, because I would like to show you the rich applicability of an asymmetric waveguide. And on purpose, you can't really see the details, because I don't want to spend time on it, because there's not enough time. But I would like to show you the flavor of how rich the SMS can become, solar magneto-seismology can become, by applying the asymmetric waveguide concept. Now, on the right-hand side, you see the actual physical environment. So, for instance, here is some loop oscillation. Here is a bridge, photospheric bridge. Here are again some loops. Here is a magnetic bright point, sunspots. And on the right-hand side, we list the various mathematical models, you know, one slab, two slab, many slabs, etc., which can describe oscillations in this medium. So, because there is so large choice of parameters, it's almost impossible to derive a general formalism for the MHD waves and oscillations. We have done, actually, we managed to describe the dispersion relation for an infinite number of slabs with various magnetic fields and hydrodynamic properties. But of course, if you want to make an application, then you know, you really have to, if you have an infinite slab, then you have an infinite size of eigenvectors, and that is not solvable exactly, at least not to the best of our knowledge. So if you make an application, you really have to trim down the application of what are the essences, what is the, how many slabs or how many waveguides you need. Then you identify the magnetic fields there. Maybe there is magnetic field in the outside medium. Maybe there are two slabs and no magnetic field in between them, etc., etc. You know, the choice is pretty large. And then
Robertus, yeah, 5
Yes?
minutes. 5 minutes are left.
Thank you. And then you can carry out magneto-seismology. Okay, so this is just to demonstrate how wide this problem is. Now let me bring me then to the issue of Alfvén waves. So the Alfvén waves are a very specific waves because they are purely magnetic oscillations. Yes, Alfvén waves do not disturb density. Alfvén waves cannot be observed in intensity oscillations. If people report this, and unfortunately, some colleagues still do this, although we have discussed this many, many times. Alfvén waves are oscillations within magnetic surfaces. As you can see here, this is a slab geometry. I have just chosen 4 or 5 cylinders, and Alfvén wave oscillations are perturbations within these slabs. And Alfvén waves only perturb magnetic field and velocity, one component of magnetic field and one component of velocity. If you observe more than that, you cannot call these waves, unless you identify explicitly the magnetic isosurface, you cannot call these waves Alfvén waves. This is wrong, this is misleading, and I think we have to be very careful. If we go further with complexity, I will show you one more on this Alfvén wave business, these ones and these ones. Of course, we can have this, on the left-hand side, I have got the m equal to 0 Alfvén wave, the traditional Alfvén wave. But on the right-hand side, I show you now 2 examples of the m equal to ±1 Alfvén wave. The result of them could be, for instance, a light bridge. And that's exactly what we managed to actually very recently publish. It took us around 4 years to convince Nature publication that the observation is right. And finally in 4 years. So the young generation among the audience who like to make probably big contribution, please think about it. It takes a lot of time sometimes to convince referees. In this particular case, we had 7 referees because of all these challenges. And it took us around 4 years, or maybe even longer than 4 years, to finally publish the paper where we convinced all the involved referees and the editors that we do see the m equal to ±1 Alfvén waves. Okay, let me go to the end of this talk because I would like to spend a minute on, you see how much stuff I leave out. I would like to come to this part. Okay. So this part of the talk, so far I have spoken about waves and how these waves contribute to heating. But now I believe that although waves have a massive amount of energy flux, I don't think that waves are probably the key contributors to heating. And this this is really puzzling me in the last 2-3 years, to be honest. In the waves, I already see much more energy than needed to heat the chromosphere, even the chromosphere. And on top of it, now we observe one particular stuff, and these are the swirls. What you can see here is it's a satellite observation. It's a Hinode observation, and we have identified the swirls. And we detected a massive amount of swirls, yes? 500,000 at every moment of time. And these swirls at photospheric level. Then if we go a little bit further up in the chromosphere, and I'm going to skip the statistics because no time for that, in the chromosphere, we have very recently also observed these swirls. In fact, even more swirls we have observed in the chromosphere than in the photosphere. So how it looks like that the solar atmosphere at small scale is full with swirls. If you go on the web and you go on the NAO or the National Oceanic, I don't even know what's the exact spelling, the American Oceanographic Institute, and you see the satellite observations of swirls in ocean, you will actually see that our oceans are full with swirls, 100%, filling factor is 100%. I was really surprised. I did not know that. I knew about the Gulf Stream, I knew about the Labrador Stream, but I didn't know that the oceans are full with swirls. And it looks to me that the solar atmosphere is the same as the ocean. It swirls everywhere. Now we have estimated the energy of these swirls, and it looks that these swirls have, again, a very high portion of energy, kinetic energy, and it's not, I'm not even talking about magnetic energy, obviously they also have magnetic energy, a very high portion of kinetic energy. Obviously, where do these go? Swirls leave just a few seconds, maybe 100, 200 seconds. After that, they die. So where does the energy go? Obviously, they go into heating. So I think these are the dark horses. It's a lot of open question. It has opened up a lot of questions what I can't even answer, and maybe in a year or two, if we have the opportunity to give another seminar, maybe I will know more about it. Just one paper has recently been published on the swirls issue. Now we have another paper under review, but we will see whether we succeed with this or not. Okay, I'm sorry I skipped this. Just in summary then, that to summarize, waves and oscillations are very important in solar physics or in plasma astrophysics because partially waves and oscillations can carry energy from place A to place B, partially because waves carry information about the medium they propagate in, and you can invert that. These are the two big questions and the two big aspects. And on top of it, I also believe now that there is one particular dynamics in the sun which has not been looked at too much, and these are these rotational small-scale motions which have even more contribution to atmospheric dynamics than we would think. And that's where I would like to stop, and thank you very much for your attention.
Okay, thank you, Robertus, for a very nice talk. Now I would like to request audience to please raise your hands or type your questions in the chat box if you have. So let me see. Okay, so Rajguru, please unmute yourself and ask your question.
Hi, can you hear me, Robertus?
Hi, Paul. How are you?
Hi. Hi, I'm fine. Good to see you. So, Robertus, can you just explain a little bit more on the chromospheric swirls? The slide you showed, you had two bottom panels showing the green contours.
Yeah.
Just say a little bit more on the detection method in chromosphere?
Yeah, so what we did, we developed a method. It's called OSDA. It's an automatic swirl detection algorithm. It's an automatic swirl detection algorithm. We tested it on numerical simulations. We tested it on specific swirl data where we have seen the data, where we have seen the swirls explicitly by eye. Also, we tested it on controlled numerical experiments. And when we were satisfied that the software identifies 99.9% of the swirls, then we have let run the data on the software on satellite data. Initially, we let it run on photospheric data, and that was our first surprise to see how high number of swirls we have seen in the photosphere. But then you ask the question, what happens to these swirls in the photosphere, especially by being involved in the paper we wrote with Sven on the Alfvén waves in 2012, where we have shown how emission in the corona appears after the appearance of swirls in the chromosphere. So, with other words, Alfvén wave propagation. And we had this knowledge, obviously, and then we said, okay, what happens to these swirls? Is there any chromospheric counterpart? Then we took chromospheric data and again, satellite data, but we can also take ground-based data, and we run the software, and we found that there are even more swirls in the chromosphere than in the photosphere. And that raises a very interesting question.
Yeah, how do you explain that?
One sec. There was one more aspect that we wanted to see whether the swirls actually do propagate from the photosphere into the chromosphere. Yes, this was a question, and we have seen that many of them do, but not all of them. And of course, we have shown this. So the time lag between the appearance of a photospheric swirl and the chromospheric swirl was exactly the speed what you need for an acoustic magnetoacoustic wave to propagate. But in the chromosphere there are more swirls, and we believe that if you have your theory, please let me know. But we also think that we may understand why we have more chromospheric swirls. But go on, please.
Yeah. So you have almost double the number. In your example, you showed almost 2 times the chromospheric swirls than in the photosphere.
Correct.
So the conventional understanding is that there are photospheric motions which twist the flux tubes and they transfer the swirly motions to the chromosphere. But then you don't have enough photospheric swirls to explain all the chromospheric swirls. So is it what is the current understanding? How do you explain them?
For that, just wait a little bit until our paper is accepted. But we believe that it's related to the jets. So jets are going to generate more swirls. That's the key word.
Or Robertus, on the similar lines, is it possible that maybe instead of comparing numbers, we should compare the energies? Is it possible that you have like one swirl at the photosphere and then it propagates to chromosphere, and then it can also bifurcate into 2 different swirls? So instead of numbers, if we look at the energies, then could a better comparison be made?
Very good point. I wouldn't call it bifurcation. I would call it splitting. You're right with that. We have done this. We have shown this in an APJ paper. I think the first author of that paper was Ben Snow, our postdoc, who is now in Exeter. And we did have a study like this. We don't have the observational. So we looked into the appearance and location of the swirls, yes, to see whether you could, you downgrade a little bit the size of the swirl, and so the 2 swirls would be seen as one. But even if you do that, you would still see more swirls in the chromosphere. And I think this is because you have this jet issue adding to, the formation of swirls. So I think it's another phenomena what we have not yet considered. So it's not the swirl itself from the photosphere just goes up, but there is another mechanism which generates these swirls.
Okay. Okay.
Okay. Thanks, Robertus.
Thank you, Paul.
Yeah. So now moving on to Ritesh, please unmute yourself and ask your question.
Hi, Robertus. So my question is related to your those slabs or wave which you showed asymmetry, one side more density than the other. What about the density variation within that oscillating slab? So how will the wave will get affected, like in case of fan loops and all?
Okay, I think this is a very difficult model to do. Even just by having asymmetry, the problem is hard to track analytically. Now, if I add to this inhomogeneity, continuous inhomogeneity, instead of having discontinuities in the physical parameters, if I would add to these jumps in the density or temperature, if I would add continuity, then I would end up what is called resonance. And I think to study resonance in a medium which has two resonant layers or more than one resonant layer mathematically is not very easy. I think Deepu may know this a little bit because he was in Leuven and it's impossible not to have a talk in Leuven on resonance, so he probably knows this, that it's a very, very difficult subject. Okay. So I would say, yeah, if there is a young giant with good math skills, we can look into it. Once we looked into the two-layer problem many, many years ago, but it's really not easy. Okay. Yes. I imagine if you have more than two slabs, then that's tough.
So I'll take a question related to this from the chat box. So Rakesh is asking what percentage of the seismologic results will differ if you consider asymmetric waveguide instead of a symmetric one? I mean, what all differences have you seen, let's say in time periods and in periodicity, amplitudes?
So to use this in practice, you really need high resolution, spatial and temporal resolution. Now we don't have that many observations which are high resolution. Dayquist is just started to operate and it's not easy. I don't know if any of among the audience wanted to get observing time on Dayquist. It's not easy at all. I have to say, from a British perspective, although we paid, we contributed to Dayquist, we didn't have enough. We didn't get the time what we thought we would get. That's just to tell you how difficult it is to get time. Now with SST, it's not easy to observe this asymmetry. We have one paper where we have addressed this. For instance, you could study the amplitude dependence as function of distance from the waveguide. If you have a coronal loop, you could study how the amplitude, as you go away from the surface of the oscillation, how that decays. But again, people who do these sort of things, like Deepu or Abhishek, or I don't know who else is on this talk, is involved in these type of things, they know that it's very, very difficult to get that resolution that you would be able to identify asymmetry at both sides of a waveguide. So we need, but the signatures are there. It's very clear that asymmetry is there, because why should be one granule having the same density as another one, or the same temperature, even if it is just 50% different, the density, or a factor of a third or a quarter, or then you already have a rather different output in terms of oscillations, and then the energy capabilities, the energy carrying capability is different, and all that stuff. So not easy. The answer is not easy, but I hope that soon, if you build your telescope in India, the National Large Solar Telescope, NLST, that will be a perfect instrument to test this theory.
Okay. Piali, please go ahead and ask your question.
Yeah. Hi, Robertus.
Hi, Piali.
Yeah. How are you? And how is your telescope?
Which one? Oh no, actually the rest of the colleagues. The reason why I'm in Hungary, not because I love heat. It's, guys, trust me. In this room, I think it's now 40 Celsius. I'm sweating, not because of the talk, but because of the bloody temperature. So we came here now to work to continue the building of our telescope, which is going to provide the needed routine chromospheric magnetic field observations. It's called SOMNET, Solar Activity Magnetic Monitor, and we have finished the construction of the instrument. It's a magneto-optical filter instrument that is done, and now I came here to oversee a little bit the actual construction of the building. What's on top of an observatory, on top of a water tower. It's a 46-meter tall water tower, and it is my understanding that this is the second highest, or probably even the highest solar telescope on Earth in terms of above the surface, not from ground level, because obviously, there are many observatories who have taller, what are higher, but from the surface of the Earth, 46 meter is pretty high.
Oh,
And
that's higher.
yeah, so we are working on it. And I have to say that there is no elevator. The elevator is broken. So, those who know me, I'm a little bit overweight. And going up 46 meters in 40 Celsius is not an exercise you want to do every day.
Yeah, okay. Okay, so now for the question. So, yeah. So I would like to ask you about this point A23, about this sausage and kink modes. I mean, I'm sorry, you already said that you don't have a number. I'm not asking for a number. What I would like to know that why is it that when you look at Hinode observations or even simulations, the model simulations that are available, specule simulations are available, it is so easy to detect or see by eye the transverse oscillations, the transverse kink oscillations, but it is so difficult to spot the sausage oscillations. So I mean, do you need a special eye? I mean, like you say that the sausage modes are dominating over the kink modes. I mean, why is it that I don't see it in simulations then, or even observations? It is not so obvious to the eye.
Yeah, I think it is there. I don't know if I have it in the presentation. In this presentation, I'm just trying to find. Let me see.
I think it was 832 question, 823. I don't remember the slide.
Can I still share my screen? Wahab?
Yes, you can.
Yeah. I clicked the wrong button. Wait, share the screen. And hold to shift, share. Okay, Piali, do you see this now? This.
Yes.
Yeah. So what you see, so here is a movie where you have only the kink oscillation. Yes, you see it now?
Yes.
And then this is a movie here where you will only have sausage oscillation. Okay? When you add the two together, this is what you will have. So here is a time distance image. Let me go back one slide. Okay. Do you still see this?
Yes.
Do you see yes. So this is a typical Hinode observation. Yes. Once Tsuneta-san, oh no, this is not Hinode. Sorry, this is ground-based. Tsuneta-san visited me, and I showed him this observation, and he asked me, "Oh, when did you get the Hinode time?" I said, "I didn't get the Hinode time." I said, "Well, this is Hinode resolution." I said, "No, it's not Hinode. It's ground-based." So from ground-based, we made the observation. Then we put a slide on it. I don't know whether you see the slide here. Yes. Here, yeah.
Yes, I can
just
see
the
that.
next slide, and then you plot it. Here is the time distance image, right? Do you see all these plenty of waves? Yes. Now, do you see it?
Yes, yeah.
Okay, so let me just go here, and here the result of so what we showed is widening, and so that if you put a slide across the of a spicule, basically. Yes. Then you will see not just the kink oscillation, as you can see it on the right-hand side. Let me stop this because this is disturbing a bit. But also you can see the contraction, expansion. You see contraction, expansion, expansion, contraction, expansion.
But it also looks like it has this asymmetric kink that you showed later on, right?
There is a bit of asymmetry in this, but at that time, when we did it X years ago, we didn't even think about asymmetry. Yes, it is asymmetry. Probably there is asymmetry. And if you look at our Frontiers paper 3 years ago, 2 years ago, Matthew Alcock, I think, is the first author. He was a PhD student with us. And we analyzed, I think, 50 of these things, and we tried to use the asymmetry theory, and we even tried to work out what's the amplitude ratio on the left and the right hand side of the waveguide. So there was some diagnostics about this, but the main point is, to come to your question, that there are sausage waves. You just have to have the right high resolution observation. Now, you were asking, why don't you see them in the simulations? My answer to that is purely, and I'm going to stop now the sharing just that I can see you. My answer to that is that it depends on what type of simulation you have. If you drive the system in 2D, you shake, you will not have it. But if you drive your system in 3D, like your genius student can do, right? Yes, you will see.
He's also here, I think.
Is he here? I don't know. I can't see the people.
So don't say that too loud.
Oh, I withdraw it. You're very nice student. You're hardworking student. Let's say this way. You know, if you run the system in 3D, you will see the sausage oscillation. I'm pretty sure that if we would take a slice across one of these 3D simulations he has got, and you do the technique Raoul developed, how to identify the sausage waves, you will see them. It's a bit of laborious to identify, but you will see them. In observations, we did this, and we found plenty.
But I was thinking that since kink modes are so easily seen, maybe they are contributing more to the, whatever dynamics.
That's the perception. But if you carefully take out the kink, they do contribute. But you work out the numbers, you work out the amplitudes. It looks that the kink oscillation flux is maybe not as dominant as the sausage oscillation for the modules what we studied. And I think we studied like thousands of them. If I remember.
I see. Okay.
That's not a theory. That's a statistics from data. Which we published it in 2012. It's a data analysis result.
I see. Okay. Yeah. Thanks, Robert.
Thank you.
So we have next question from Dipankar. So Dipankar, go ahead.
Yeah. Hi. Robertus, you mentioned that we have not probably made too much progress in terms of the dissipation, because at the end of the day, it is the dissipation mechanism which will tell us how much energy we have. We have been able to identify many different wave modes, their properties in different ways, spectroscopy, imaging. But now I think we have to move forward, and apart from the resonant absorption theory, there are some development which is happening in terms of the turbulence thing also. So I'd like you to comment, where do we move from here?
Yes. So the problem is, Deepu, that the scales for dissipation is probably of the order of a few kilometers or maybe some hundreds of meters. And you are very familiar with observations, much more than myself. You know that is not achievable. That's the problem. So in order to resonant absorption is a nice mechanism, but whether resonant absorption will survive the challenges that will come with the improved resolution, I don't know. Resonant absorption, people have studied resonant absorption in multifluid plasma. And interestingly, the results are not much different. And this is always my argument that why do we use MHD? Why don't we use multifluid plasma? Well, the answer is for many phenomena, MHD works perfectly. And I don't mind to share with all of you, we submitted a so-called European Research Council Advanced Grant, yes, 4 of us. And we got 16 referee reports, 16. 15 said outstanding or excellent. 1 said reject. Now this one said reject because we use MHD, and the person in the referee report said that we should wake up. This is 20th century, end of 20th century, and we shouldn't use the obsolete MHD framework. And you know, first of all, this referee report is not helpful, so forget that. But the problem is that actually it's not correct, because the MHD is a pretty good approximation. It works way beyond how it should work. In the solar corona, we can explain very nicely, and we know that the solar corona is a highly collisionless plasma, but still the MHD framework works properly. You know, it's like the asymptotic theorem or the Taylor expansion. You know that sine x is x, and you replace sine x very often with x when you Taylor expand, and you know that is not exactly correct. And sometimes you are wondering why this still works up to 20-degree oscillation, although the sine x can be replaced by x up to 5 degrees on, but it works. So for some reasons, MHD is a good approximation, and I don't think that all these efforts people put into the multifluid plasma, this does not seem to change the dynamics. That's one comment. So I would not move away from the MHD. The second thing you mentioned the turbulence. That's, I think, is a difficult concept, but it's mathematically very difficult. I don't do turbulence because I don't understand. I have my limits. You know, linear theory I can do. Nonlinear, it's already difficult. Turbulence is highly nonlinear. I think in order to do proper turbulence study, we need numerics. It's a numerical issue. And do we have the computer power for that? Not yet. I mean, maybe in 5 or 10 years we do have. I mean, we do have already nice codes who do turbulence, but and individually we also have turbulence very often in our MHD simulations. You know, up to some level you can do it, but in 3D turbulence with solar application, with the stratification, we have forget it. So you are right. Maybe turbulence is the way is a way which will help us to make progress. But I think, and I would like to go back to a point, I think once we understand the jet wave interaction, that will already be a big progress. So if I was if a new student would come to me, I would say try to look into this aspect, you know, the jet, the local jet, the jet study, because jets and swirls we see everywhere. Yeah. That's the big thing.
Yeah, incidentally, we projected this, you know, jet being responsible for wave generation. Tanmay did quite a bit of his work in the PhD period on that. Yeah.
Oh, very good, very good.
Yeah, but there we said slow wave, but I think here Robertus is talking about also kink waves generation by spicules or jets, right? That's what you are saying.
Or Alphen waves, even
all
more.
Alphen waves, yeah.
So it all depends on the orientation and what geometry you take. You know, I mean, just generating a compressional wave is easy. You just need a piston, but you don't have to worry about the orientation and symmetry and all that.
Can I just correct you a little bit? So we should not distinguish the waves as kink or sausage. We actually should distinguish between slow and fast or Alphen. That's the right distinction. And whether a slow wave is kink or sausage or whether a fast wave is kink or sausage, that's another question. But you know, just to clarify this, that
no, what I meant is what I meant is not the sausage wave, but the slow waves or the propagating disturbances. That was something that Tanmay and we did.
I mean, particularly, you know, as you know, I mean, if you are limited by primarily imaging observation, and when you see density compression, you see intensity changes, you interpret that as a compressional front. And if the wave speeds are lower, you term it as a slow.
I mean that is equivalent to tube speed, but then along the magnetic field lines it reduces to the sound speeds. And okay, so I mean, let me wrap up fast. So there is one question by Santosh, and he's asking, does magnetic field responsible for stratification?
Sorry,
does magnetic field responsible for stratification?
Absolutely.
And
That's the short answer.
there's last question by Samrat, and he's asking what makes chromospheric swirls move faster than the photospheric swirls?
The short answer is that plasma beta. So all the density. Yeah, Alpha. Okay, very short answer. Alpha speeds are much larger. Characteristic speeds are much larger there than in the photosphere.
Yeah.
That's the short answer. You know, plasma beta is dropping exponentially, and because of that, sound speed is higher, cube speed is higher, alpha speed is higher, etc., etc. So you will have a faster propagation.
Yeah. Okay, then final closing remarks by Dipankar. And yeah, please, Dipankar, go ahead.
Thank you, Vaibhav, for arranging this seminar. And thanks, Robertus, for a very nice talk. I was watching that at one point we had 58 people on our Zoom room. I don't know how many are there in YouTube and Facebook Live also. So you're a very popular speaker in India. As you can see that people from quite a few other institutes have also joined today to hear you. And I will be really happy to host you here as and when things are possible. We can have a face-to-face seminar and the post-seminar chats, which is we are missing very badly.
You know, Dipu, we also try to host you because you are the external, but now it's for one of the Vivas, but it's not possible to travel. I mean, if you want, you can, but they will put you in quarantine for 10 days and it's terrible.
Yeah.
It's terrible. Sorry.
Yeah, let me know whenever this defense is scheduled. I mean, they will be arranging it, I guess, through virtual platform. Now they will agree on that.
Yeah. I think that is already agreed. Did you get the thesis? You got the thesis, right?
Yes. I think they send me some links and all that. Yeah.
So then Ruderman is the internal, so he has to set up all these time schedules with you.
Okay.
Thank you very much for this very nice thing. It's really good that we can do these things remotely in some aspects. Good.
Yeah.
And
something is better than nothing, so that way.
Thank you for everyone's attention who could come, and I can see many friends and I recognize names. So thank you for all of them for coming, and to you as well for inviting, and to iHub for organizing.
Thank you, Robertus. And yeah, okay, so thank you everyone for joining. So see you next week with a new talk. Bye, Robertus, and bye everyone.
Bye.